3, day 4. So we've been talking about a lot of different functions recently, very specific functions, but now we're going to talk about sort of combinations of functions. Okay, so these first ones, function operations, that means we're just doing different kinds of mathematical operations between different kinds of functions. This, by the way, is called function notation. When you name a function and you put like an input value into it. So this means that you just got to use the correct function. 4 cubed is 64. Square root of 36 is 6. Final answer is 58. Now you can actually put functions inside of other functions. Those are called composite functions. So that means you got to work from the inside out. Order of operations, you got to do F4 first, which is 64. And then G of 64 is square root of 64 is 8. Right? This means the same thing. This F little open dot, that means F with G of 9 inside of it. So just another way of writing that. G of 9 is 3. 3 cubed is 27. Final answer is negative 19. Now this is called the difference quotient. And it's just another example of function operations, but it's something significant that we will be encountering in calculus quite a bit. So in calculus, we spend a lot of time using this. But anyways, simply it is just the slope of a function. It's just rise or run, change in y over change in x. So if you're to plug x plus 3 in and x, that's your change in y, and then x plus 3 minus x on the bottom, that's the change in the x's, that's your run. It gives you slope. But, for instance, right here, x plus 3 minus x gives you 3, right? So for now, you don't need to know what that is other than, okay, we could plug that in. We could plug x plus 3. So you can plug actual expressions into functions. So x plus 3 squared plus 2 times x plus 3 minus, now you want to be careful here because you want to subtract. We're going to plug x into this and we need to subtract all of it. Now when you plug x in, you just get what you see right here, but we're going to have to distribute this subtraction. Okay? It's an easy mistake to make. All over 3, don't forget the denominator. Now let's see if we can clean it up. If we FOIL this, we get x squared plus 6x plus 9 plus 2x plus 6. You got to distribute that. Minus x squared minus 2x all over 3. The x squareds actually cancel. These 2x's cancel. So we have 6x plus 15 left over 3. And the final answer would be 2x plus 5. So now another way of combining functions, and we've talked about this a little bit, is with what we call piecewise functions. Piecewise functions are functions that are defined with one shape, one part, and another shape, another part. I think we did some of these back in Unit 1. So what I would do if I were trying to sketch them is just sketch both of them completely. So this is a parabola, by the way, right? And I think to get a good graph of this, let's find its roots. So let's find its x-intercepts. Those seem pretty important. -6, 0, and it's opening up. So I don't know, I'm going to do this lightly because it's not my final answer. I'll darken in my final answer. So something kind of like that is the parabola. And then the other one's a line that goes through -4. Y-intercept has a slope of 10. So up 10, 1, 2, 3, 4, 5, 6, over 1. And then it keeps going. Now, this graph doesn't look great yet. I mean, we could just kind of We'll go with that. Now, I might, and that should be light. Now, at x equals 2 is where you change from one function to the other. So you should probably find what's the value of 2 for both of them. So if you plug 2 in to the parabola, you're going to get 4 plus 12 is 16. And you plug 2 in this line, you get 20 minus 4 is 16. So they actually both cross at x equals 2. So I'm going to just kind of force this and say, okay, this is 16. Now, for the parabola, it's going to be everything to the left, and it's a solid dot. So to the left of 2, you're using the parabola as that piece of the graph. And then to the right of 2, it's an open dot, but it's right on top of that closed dot. And then you're using the line the rest of the way. Now, the open dot you can't see because it's right underneath the closed dot. So might label which one is which. Anyway, so that's a piecewise graph, and we run into this quite a bit in calculus. And it's not a calculus idea on its own. Now, one interesting thing is that these graphs were connected, okay? So here's a question. Is the graph continuous, differentiable, both, or neither? And this is a common kind of question on the AP test. So continuous, we'll talk about what these means. These are some sort of important ideas that we use in calculus quite a bit. A lot of rules and theorems are based off of some of these things, or both of them being true. Continuity, in sort of like simple terms, means that the graph is all connected. Okay, that you could, in even simple terms, that you could draw the graph without lifting your pencil. Okay, so to get from one chunk to another, because we're going to get a lot of graphs that are broken up. If you have to lift your pencil up to get from one piece to another, then it's not continuous. So continuity means continuous. Continuous means no breaks, right? Discontinuity, some examples of discontinuities are a point discontinuity, which is sometimes called a hole, an infinite discontinuity, which is sometimes called a vertical asymptote, and a jump in the graph. Okay, so a hole means that there's literally a hole in the graph, and you can't say, oh well, I could go around this without lifting my pencil. No, that doesn't matter. Holes actually don't have any borders. We just draw them so you can see them. Points don't have borders. They're infinitesimally small. A vertical asymptote, we've seen graphs like this, might look like that. The graph gets broken up. You can't go from this side to that side without lifting your pencil. A jump would be something like that, where there's like an actual break in the graph, and it dramatically jumps to another place. Now, one way to sort of help, we graphed it and we could tell that this was a continuous graph, that these two pieces actually connect. There's not a hole, because even though one's open, the other one's closed, so together they make it close. There's no jump, there's no vertical asymptote. So this graph shows you that's continuous. Another simple way, not a technical way. So a simple way, not a technical way, but one way that kind of works a lot of times, is to just plug the point that the point you should be worried about in this graph is where it transitions from one piece to another at x equals 2. So x equals 2 is the point of concern most likely. I mean, there's discontinuities that come up in other places in the middle of the function, but if you're putting two functions together, like where you put them together is a hot spot. So we can plug 2 into each of them. 2 into the first part. And we kind of did this earlier. Get 4 plus 12 is 16. And then you plug 2 into the other one. Now, technically, we're not really supposed to be plugging 2 into the other half, because it's not defined for when x equals 2. It's only when x is greater than 2. But this will do the trick. 10 times 2 minus 4 equals 20 minus 4 is 16. And if these are equal, then that's a good sign. They're probably attached right there. So another idea is that that's what it means for a graph to be, or a function to be continuous, or for continuity to exist. Another one is if a graph is differentiable. And differentiable is a fancy word for the derivatives existing everywhere. In simple terms, it's like a roller coaster. You want nice rolling curves, okay? So, something like this. This is a differentiable curve, okay? You don't want any corners like this. Like that's bad. Corners or a cusp or something like that. Think of on a roller coaster, that wouldn't be good, right? But that's sort of the basic idea. It's got to be nice and smooth, no corners. Now, what causes a corner to happen? Here, when we drew this, it almost looks like there's a slight corner, or is it perfectly transitioned? Well, it was a rough graph, but there's a way for us to determine it without graphing it perfectly. The idea behind a corner or a smooth graph is the slopes are gradually changing from one slope to another. No, nothing drastic, but here the slope is going from here to here, and that's if you get a sudden change in slopes, then you're going to get a corner or some kind of sharp piece of graph. So the idea behind it is slope. Now we can actually take the slope we can find a slope function for a piecewise function, a derivative, k prime. So we could do the derivative of each part, 2x plus 6, power rule. When x is less than 2, I'm not going to put the or equals yet. I'll tell you why in a second. The derivative of the next one is 10, just 10, when x is greater than 2. Now, a way to determine if there's a nice smooth transition at that x equals 2 point, which is probably what we're worried about, is to plug the x value in. So we could plug k prime 2 in to the first part, and we get 10, and k prime 2 into the next part, and we get 10. And if they have the same slope, then that's a great sign. Now we're allowed to go back and put the or equals to, because if they didn't have the same slope, that means there's a corner, and technically the derivative, the slope, does not exist at a corner, because which side are you going to pick? Or, like it's a sharp point. So you can't really say, well, what's the slope of this really sharp point? There is no slope because the two sides aren't the same. Now, there's this requirement, though, that for you to have a smooth graph, it has to be continuous. You can't be like, oh, well, the slopes are the same, but there's a jump. Well, that's not smooth. Think roller coaster example. That's not good on a roller coaster, right? If it's not continuous, then it's not differentiable. So you actually have to look at the the continuity also. Now, one of these answers up here, this graph was continuous, it was differentiable, so it was both, was the best answer, okay? One of these answers would never make sense on its own. Just being differentiable is not possible without it being continuous. So answer B is just logically impossible. So it can't be answer B unless it's also answer A at the same time. So you would have to pick both. Now, just as an example to kind of show you how something could work, if you change the 10x minus 4 to 12x minus 8, so I'm essentially redefining the function. Actually, so I was going to change this to 12x minus 8. So we would want to check for the continuity. And by the way, we could just kind of leave it in sort of this piecewise sort of notation. And 4 plus 12 equals 16. And here, 12 times 2 minus 8 is going to be 24 minus 8 is 16. So that's good. It's continuous. And then k prime for this new piecewise would be 2x plus 6. And then this would be 12. And if you were to plug in 2 into this, you get 10 and you get 12, which are not equal. So it's not differentiable, right? It is continuous. So it can, if it's differentiable, it has to be continuous at the same time. If it's continuous, it doesn't have to be differentiable. So it would be continuous, but not differentiable. Anyways, let's see. I thought, okay. On the back, we have another common thing on the AP test. It's called a function table, and it's really just a way of organizing information about multiple functions all together in a really nice kind of structure. And also, it avoids giving you the actual functions, which allows you to be tested on certain ideas without getting into all the possible ideas. So these are the inputs. These are the x values that we're plugging into these functions. So these are the outputs, or like the y values of the functions. So it's really just a bunch of information very compactly stored. So g of 3, you'd say, well, here's g, here's 3, here's g of 3 is 4, right? And it's 4 here again, and it's 20, and then k of 4 is 2. So the final answer is 18. So it's kind of an interesting, different way of giving you information. Now this one's interesting. Find all x such that g of f of x is 3. So what we're doing here is we're actually solving an equation, but without any real function. So how do we solve the equation? Well, you kind of want to work backwards when you're solving, right? So you want to figure out, well, what would you plug in to g that would give you 3, right? You'd say, well, g, when is g equal to 3? Oh, when you plug 0 in. So g of 0 equals 3, right? Well, that means that whatever's inside g has to be 0. So f of x has to be 0. So you say, well, what do you plug in to f that would give you 0? In f, 2. So your final answer is x equals 2. Now, these are solving equations, so it makes sense to use variables. So anyways, that's kind of a weird way of solving equations with the table, kind of working backwards table. All the known zeros, well, that means that this has to equal 0 for the whole function. These are like the x-intercepts, the roots, right? So we want to say, first start with the outermost and say, well, what do you have to plug into k to get 0? So you look over here and you say, well, you plug 0 in. So that means that f, we got to figure out, well, f is the next one. We need f to equal 0. When does f equal 0? When you plug in a 2. Okay. So then you're trying to figure out, well, how do I get a 2 out of g? G equals 2 when you plug 2 into it. So the final answer is x equals 2. Coincidentally, the same as the last one. But so this can be, maybe a little challenging first. Domain. Now we start talking about domain with logs, but there's lots of functions that have domain issues. And we need to watch out for them because it's often going to be impact your answer, and no one's going to tell you, hey, watch out for the domain. You can't give answers where the domain doesn't exist because the graph and the function doesn't exist there. You can't tell me there's something true about a graph if the graph isn't even there. So rational functions, the thing you really got to watch out for is for the denominator can't be 0, because if you divide by 0, it's undefined, right? So, we could factor this: x minus 6, x minus 2, x minus 4. So it's really the bottom that can't be 0. So x can't be 2 and or 4. So the domain's everything else. Sometimes they might kind of describe the domain by saying what it can't be, which indicates it can be everything else. But we're going to go with interval notation. So it's going to be negative infinity to 2, 2 to 4, and 4 to positive infinity. So this is describing all the values of x that you're allowed to plug into this that don't cause problems. So there's vertical asymptotes here, right? If you get division by 0, it could be a vertical asymptote. Could be a hole in the graph too, but I don't know if we talked about that yet. Even roots, square roots, fourth roots. You can't take square roots, fourth roots, whatever, of negatives, right? If you do, you get imaginary answers, which do have very real applications. But we're not dealing with those. We're dealing with the real numbers. So you'd have to say, okay, well, the inside of this needs to be greater than or equal to 0. So the inside of this has to be greater than or equal to 2. And as interval notation, that's going to be bracket 2 to positive infinity. So this is kind of like what we were doing the other day with the logs, is saying, well, here's the restriction. So let's say, okay, well, the inside has to be greater than or equal to 0. Whoa, this one has another issue. X cannot equal negative 1 at the same time. Okay, now we could do a line check for this. Now we're not doing true false. Yeah, I guess we're doing true false. We say, okay, well, x equals 3 is a solid dot. The inside can be equal to 0. With logs, it can't even be equal to 0, but with these, it could equal 0. Open dot negative 1, test a value. I'm going to test far right. 4, positive true, false, true. And so there's a visual picture of your domain, but we need right interval notation. So we're doing these line checks a lot. Logs, like we already talked about, can only take logs of positives. Okay, so negatives are out, 0 is out. So the inside has to be greater than 0. So you could, sometimes it's easy enough to solve. It's a linear inequality, which you don't need to do a line check for. But sometimes it gets more complicated. So the inside has to be greater than 0. So this is going to be a line check thing. Negative 4, 2. So x can't be negative 4, but it needs to be on your line check is an open dot. That's why it's an open dot. 2 is going to be open dot. I'm going to test a value. X equals 3. It's going to be positive, true, false, true. Watch out for the bounces on the graph issues too. I know we haven't seen it for a while, but they'll sneak up on you. Negative infinity, negative 4, 2 to positive infinity. Now, I thought maybe I could show you maybe like one problem from the homework. Maybe problem 15. So if you have your worksheet, show you problem 15. And this is kind of like the stuff you're doing on the front of the page. So here's a piecewise function. Now this is related to what we're doing. It's not exactly like it, so that's why I want to give you one. So it's find m and b so that g of x is always continuous and differentiable. So we want to make it continuous and differentiable. So if you want something to be true, then a lot of times what you're going to do, I mean, this, by the way, is a cubic, something like that. This is a line. And then at 2, we want it to be a perfect match, and we want it to be smooth, right? That's our goal. So if you want something to be true, then you act like it is true. So for this to be continuous, the y values need to be equal to each other at the transition, right? So you say, okay, well, the y values 2x cubed must equal mx plus b when x equals 2. So we're going to plug 2 into this, and we're going to get 2 times 8 is 16 equals 2m plus b. So this is one thing that we know has to be true. For it to be differentiable, the slopes have to be equal to each other, right? The derivatives. So that means that 6x squared has to equal m, right? The derivative of 2x cubed is going to be 3 times 2 is 6x squared power rule. Derivative of mx plus b, the slope of the line is m. And this specifically needs to be true when x equals 2, not all the time. So you plug 2 in here and you get 24 equals m. Well, there you go. There's half of your answer. M has to be 24, and then you can plug it into this. You essentially get a system of equations. Pretty easy one, though. And there you go. So, we're going to be, doing problems like that. So try the rest of the homework on your own. Check your answers. And these ones are trying to sketch these piecewise functions. Just, I don't know, try and do as good a job as you can. I'd sketch all of the functions together for each piecewise and then lightly and then darken them in. So there you go.